Introducing the spectrum in vibration analysis, understanding frequency components for mechanical diagnostic. What is a vibration spectrum? Why use the spectrum instead of time waveform? A vibration spectrum is a graphical representation of vibration amplitude plotted against frequency. Unlike a time waveform, which shows vibration over time, the spectrum provides a clear view of how energy is distributed across different frequencies. This transformation from time domain to frequency domain is achieved through the fast Fourier transform (FFT) algorithm. The spectrum is essential because real-world machines generate complex vibrations composed of multiple sources such as shafts, bearings, gears, and blades. Each source vibrates at its own characteristic frequency, and when combined, these signals create a waveform that is difficult to interpret. By converting the waveform into a spectrum, analysts can isolate individual frequencies, making it possible to identify specific components responsible for vibration. This approach is the cornerstone of modern vibration analysis and condition monitoring programs, enabling early detection of faults like imbalance, misalignment, and bearing defects. Understanding the spectrum is critical for diagnosing machinery health accurately and preventing costly failures. The time waveform becomes increasingly complex as multiple vibration sources interact within a machine. For example, a motor may exhibit vibrations from shaft rotation, bearing defects, and gear mesh simultaneously. In the time domain, these combined signals appear as an irregular pattern, making it nearly impossible to distinguish individual contributors. The spectrum solves this problem by separating these signals based on frequency. Each peak in the spectrum corresponds to a specific forcing frequency, such as one-order shaft speed or blade pass frequency. This separation allows analysts to pinpoint the origin of vibration and assess its severity. Furthermore, the spectrum facilitates trending and comparison against established standards, such as ISO 10816, which define acceptable vibration levels. By focusing on frequency-specific data, analysts can identify faults early, plan maintenance proactively, and avoid catastrophic failures. In short, the spectrum transforms complex vibration data into actionable insights, making it indispensable for effective machine diagnostics. The role of FFT in spectrum generation, how FFT separates complex signals. The fast Fourier transform, FFT, is the mathematical process that converts time-domain vibration signals into frequency-domain data. When a machine operates, sensors capture continuous analog signals representing vibration. These signals are digitized into discrete samples, forming a time record. The FFT algorithm then decomposes this complex waveform into its constituent sine waves, each with a specific frequency and amplitude. The resulting spectrum displays these components as peaks along the frequency axis. The resolution of the spectrum depends on factors such as the number of samples, sampling rate, and maximum frequency, max, selected during data acquisition. Higher resolution provides more detailed frequency separation but requires longer sampling times. Analysts must balance resolution with practicality to ensure accurate diagnostics without excessive data collection time. Understanding FFT and its influence on spectrum quality is vital for reliable vibration analysis, as it determines the clarity and accuracy of the frequency information presented. Machines produce vibrations that are combinations of multiple sine waves generated by different components. FFT assumes that any complex waveform can be represented as a sum of simple sine waves. By applying FFT, these individual waves are extracted and displayed as distinct peaks in the spectrum. For instance, a fan with an unbalanced rotor and multiple blades will generate two primary frequencies, one at the shaft rotation speed, one order, and another at the blade pass frequency. In the time waveform, these signals overlap, creating a confusing pattern. However, in the spectrum, they appear as separate peaks, making it easy to identify both sources. This separation is crucial for diagnosing faults accurately. Analysts can then relate each peak to a specific machine component, enabling targeted maintenance actions. Without FFT, distinguishing these signals would be nearly impossible, highlighting its importance in modern vibration analysis. Relating spectrum peaks to machine parts, using forcing frequencies for fault diagnosis. Each peak in a vibration spectrum corresponds to a specific forcing frequency generated by a machine component. For example, a peak at one-order shaft speed often indicates rotor imbalance or misalignment. Bearing defects produce characteristic frequencies such as ball pass frequency outer race, BPFO, ball pass frequency inner race, BPFI, ball spin frequency, BSF, and fundamental train frequency, FTF. Gearboxes exhibit gear mesh frequencies and sidebands, while fans and pumps generate blade pass or vane pass frequencies. Electrical motors may show peaks related to rotor bars or winding slot pass frequencies. By comparing observed peaks with calculated forcing frequencies, analysts can identify the source of vibration and determine the type of fault. This correlation is the foundation of diagnostic accuracy in vibration analysis. Understanding these relationships allows maintenance teams to address issues proactively, reducing downtime and extending equipment life. Forcing frequencies are predictable vibration frequencies associated with specific machine components. By calculating these frequencies based on machine geometry and operating speed, analysts can create a reference for interpreting the spectrum. When a peak aligns with a known forcing frequency, it indicates that the corresponding component may be faulty. For example, a peak at gear mesh frequency suggests gear wear, while sidebands around this frequency may indicate misalignment or eccentricity. Similarly, bearing fault frequencies help detect early-stage defects before catastrophic failure occurs. Monitoring amplitude trends at these frequencies provides insight into fault progression and severity. This method enables condition-based maintenance, reducing unplanned downtime and optimizing repair schedules. Accurate identification of forcing frequencies and their representation in the spectrum is therefore critical for effective vibration analysis and machine reliability. Here is the visual chart showing common forcing frequencies and their associated machine faults in a vibration spectrum. What this chart shows. X-axis, frequency in Hertz represents the frequency components of the vibration signal. Y-axis, amplitude represents the strength or severity of vibration at each frequency. Labeled peaks. 30 Hz 1 times RPM, unbalance, a classic sign of rotor imbalance. 60 Hz 2 times RPM, misalignment often appears with angular misalignment. 120 Hz electrical, 2 times line frequency, common in motors with electrical issues. 250 Hz BPFO, bearing outer race defect, a high frequency peak from bearing damage. 275 Hz BPFI, bearing inner race defect, another bearing related frequency. 300 Hz gear mesh frequency, indicates gear tooth engagement or wear. This chart helps you visually correlate specific frequencies with machine components and fault types, a key skill in predictive maintenance and condition monitoring. Why this is so important. Number 1, frequency known as source. The location of the peak, its frequency, tells us which part of the machine is causing the vibration. Example, a peak at 1 times running speed, likely unbalance. A peak at 2 times running speed, possibly misalignment. High-frequency peaks often bearing defects. Number 2, amplitude known as severity. The height of the peak tells us how bad the problem is. A small peak might be acceptable. A large peak indicates a serious issue. How this helps in diagnosis. By identifying the frequency of a peak, we can trace it back to a specific machine component. This is how we distinguish between a bearing problem, specific high-frequency peaks. An unbalance, 1 times peak. A misalignment, 1 times and 2 times peaks. A gear fault, gear mesh frequency and sidebands. Here is the visual chart showing vibration spectrum with common machine faults. Here's the explanation. X-axis, frequency in Hertz represents the frequency components of the vibration signal. Y-axis, amplitude represents the severity or strength of vibration at each frequency. Labeled peaks. Unbalance, 1 times, at 60 Hz, a strong peak at the machine's running speed. Misalignment, 2 times, at 120 Hz, a secondary harmonic indicating shaft misalignment. Bearing defect, BPFO, at 250 Hz. A higher frequency peak typical of bearing outer race faults. Gear mesh at 300 Hz, a peak at the gear mesh frequency, often accompanied by sidebands. This diagram helps visualize how each machine component or fault type contributes a distinct signature in the spectrum, enabling precise diagnostics. In summary, the spectrum is a powerful tool that reveals the hidden structure of vibration. Peaks in the spectrum are not random, they are signatures of machine components. By analyzing frequency and amplitude, we can diagnose faults and prevent failures.